So yesterday we were talking about an object attached to a spring, and we had pulled the object out and released it. So we're in this place right here where the object is displaced a distance x away from the equilibrium position. So it has potential energy equal to 1/2 k x squared, but it also has some velocity, so it has kinetic energy equal to 1/2 mv squared. So at this moment, if I was to consider all the different things that are happening, it's got a velocity in this direction. There's a force from the spring that is also in this direction. There's an acceleration in this direction. All those things are happening. The object is speeding up right now, sure, but its displacement is in that direction. It's displaced that way away from the equilibrium position. It's currently speeding up and will continue to speed up until it reaches equilibrium. After it passes equilibrium, it's going to slow down because now you're compressing the spring. The force is going to change direction, and therefore the acceleration will change direction, but it won't instantaneously stop, so the velocity has to be reduced to zero. But I want to talk about this one place right here for just a minute and remind you that it has a total energy equal to 1/2 k a squared, because that was the amount of energy we put into the system when we pulled the box out to begin with. So if we were to write an equation for conservation of energy, we'd have the energy when it was released, 1/2 k a squared, and we'd have to set that equal to the energy it has right now, 1/2 k x squared plus 1/2 mv squared. Now this would be a standard way for us to figure out perhaps how fast it's going, if we know what the extension of the spring is or something like that. I'm not really here to try and do that. I want to show you something that we didn't do or we haven't done before. Yesterday we said that the way you get a differential equation is by focusing on force, because we know force has in it acceleration, and acceleration is a differential. Well, here we have an example of another equation, and this equation has two variables that are related by a differential as well. We have x and v. They're related by a differential, and this happens not infrequently where we have situations for energy that also involve two related differential variables. Now, looking at this one as a differential is a little bit tough because it's based on some arbitrary initial value. And here's where, learning a little bit about the tricks of the way math works might help you out. This arbitrary initial variable there is a constant. It doesn't change. And it doesn't matter how many times this thing oscillates back and forth, because the total energy in the system is a constant, we know that this sum is always going to add up to be the same number. Now, again, not a lot of help if we don't know what that number is, but based on the rules of calculus, I know that I can take the derivative of both sides. And if I take the derivative with respect to time of both sides of this equation, the left side is going to be zero. The left side's not changing with respect to time. It's staying a constant. So the left side gives me a zero in my equation, which means I'm going to be producing a new equation that does not have anything to do with time. That does not have a basis on some arbitrary constant, something that I would have to know at the beginning. It tells me something about the situation that doesn't require I know how the system started. Unfortunately, though, I do have to take the derivative of this function. So let's start here with the 1/2 kx squared. The only thing that has the potential to change with respect to time is x. So I'll have 1/2 k times, now I have x squared. So bring down the 2, multiply by the x, and then I have to take the derivative of x with respect to t. I'm doing the chain rule right now, and that's going to be dx dt. So just chain roll it out. I move the constant out front, did the chain rule on x squared, and then I'm done. So next I'm going to go to the next term. 1/2 m is a constant. I'll bring that out front. I have v squared. V does change with respect to time, so I do need to do the chain rule here. So times 2v. Now I need to take the derivative of v with respect to time, so times dv dt. Now, this differential equation has differentials in it, and they're different differentials. But if you pay attention here, first, I hope you see that 1/2 and 2 cancels out here, so I get I get k times x times, well, dx dt we know about, that's velocity, plus, all right, so my 1/2 times 2, well, that disappears, and I'm going to get just m times v, and dv dt we know, of course, is a, acceleration. Now, well, I hope you see it, but there's clearly something that can be factored out here. So and as long as v is non-zero, and in this instance we know it's not, then we can we can get v out. And get this relationship, kx plus ma equals 0. Well, that shouldn't be a surprise. That's the force equation from yesterday. So what I'm trying to put out there for you guys to see is that we have different ways of generating a differential equation. Now, this particular one generated the same differential equation, and it's not a secret why. If you're pretty shrewd, you might be able to figure out why this worked out the way it did. And if you're not, well, I want you to think about what it means to find the rate of change of energy. And maybe think that through, because there's other definitions and other ways to express that. You might be able to pick up on where I'm going there. But if not, then I want those of you who are more looking at the surface of this, not looking very deeply, to recognize that any equation that starts with differentials, it has differentials in it, in this case x and v, we know they're related to each other. Any equation that starts that way is something that you can manipulate and potentially look at as a way of generating a differential equation. And if you're going to write anything down from taking notes today, the biggest thing today that started us all off with minus kx equals ma. It was our basic differential equation. Here is that a differential equation tells you something about the way functions are related. And I know that this is, I've been harping on this quite a bit, but remember, the acceleration is the rate of change of the velocity, and the velocity is the rate of change of position. This equation tells me how the position and the acceleration are related. They take and tell us about the relationship between two functions in the same way that algebra tells us the relationship between two variables. I know that this looks like an algebra expression, but it's not. Not in the sense of the way in which we've talked about algebra in the past. This is an expression. It is the algebra of functions. It is the way in which functions are related. And it's appropriate to understand that this is going to produce x as a function of t. And from there, we should get v as a function of t and a as a function of t. By this point, you were supposed to go home last night and be able to tell me what these three things are. I even set you up with the first one. And in one class, I let this slip. In the other class, I didn't. But cosine is the better function to have here. You should be able to tell me why. And that's our starting function. So today in class, kind of my expectation is you're going to come in with the other two functions. the velocity and the acceleration, and then we're going to talk about some of the meanings here. And I know that this is simple harmonic motion, but there is a bigger purpose to why you need to see these. So make sure today when you come to class, you've got these ready to go. This video is relatively short because I'm encouraging you guys to take a moment and at least watch a little bit of the video that is coming from College Board. We'll see if they have any merit or any value. So again, come to class ready to go, and we'll get started at our normal times.